Tesla recently concluded the third quarter of 2025 with truly excellent figures. The company manufactured 447,450 vehicles and successfully delivered 497,099 units globally. That remarkable achievement is merely the start. In the following year, 2026, the introduction of the Tesla Model 2 is expected to propel these delivery and production counts significantly higher. This new automobile is specifically engineered to challenge the existing domination of the electric vehicle (EV) market by Chinese manufacturers. It accomplishes this by combining a genuinely low and attractive price with advanced driver-focused technologies that feel far from being inexpensive or cheap. What special features are cleverly concealed within the framework of this compact vehicle that allow it to perform so much better than its size and price class suggest? How is it possible for this car to offer immediate and lively throttle reaction, manage steep hill ascents with power, and simultaneously use less energy? Furthermore, why will both established, older vehicle makers and newer Chinese competitors likely face difficulties in rapidly replicating this specific design? Stay tuned with Auto Fusion as we systematically examine this car piece by piece and uncover the smart engineering that has the potential to completely reshape the entire automotive marketplace. Please subscribe to help Westech achieve a milestone of 10,000 subscribers, and make sure to activate the notification bell so you are immediately alerted about our subsequent in-depth analyses. What core elements permit the Tesla Model 2 to perform better than Chinese EVs during actual road use? First, what specific features enable the Tesla Model 2 to surpass the driving performance of Chinese EVs in everyday conditions? The Tesla Model 2 provides a distinctively sharp and quick throttle feel primarily because its electric motor is specifically designed for generating a high amount of torque for every unit of electrical power, kilowatt, it consumes, all while incurring minimal power loss. Crucially, the various parts of this advanced motor design operate together in a coordinated fashion rather than functioning as isolated components. The rotor, which uses an internal permanent magnet (IPM) structure, cleverly employs ferrite assistance and has precisely shaped flux barriers. This setup skillfully merges the rotational force created by the magnets, magnet torque, with the force created by the magnetic field changes, reluctance torque. Simultaneously, it directs the magnetic flux along very short, highly efficient paths. This clever channeling significantly reduces iron loss, which is a major source of wasted energy, particularly as the motor speed increases. This advanced rotor is matched with a stator constructed from extremely thin layers of electrical steel, known as laminations, which are approximately 0.27 millimeters thick and coated to ensure minimal energy loss. Since the energy loss due to eddy currents increases roughly in proportion to the square of the lamination thickness, simply moving from a thickness of 0.35 millimeters to 0.27 millimeters can cut that particular loss component by about 40%, assuming all other design aspects remain constant. Completing this high-efficiency picture is the system of direct winding cooling. This cooling is achieved through focused oil jets or specialized channels within the motor slots, and it safely permits a higher current density in the motor windings without causing the temperatures to rise past acceptable, safe limits. This specific change often results in substantial double-digit improvements in continuous torque output, typically ranging from 10% to 30%, depending on the exact motor setup. With all these sophisticated components and principles working in perfect harmony, the Tesla Model 2 responds immediately and powerfully to the throttle at slower speeds, maintains a powerful pulling capability in the middle speed range without requiring an unreasonably high peak power rating, and, importantly, converts a greater proportion of the battery's stored energy into actual movement instead of wasting it as heat when the car is traveling at cruising speeds. This same comprehensive approach, or systems thinking, is also applied to the braking mechanism, where better efficiency and a more natural feel mutually strengthen each other. The car uses a brake-by-wire system that precisely measures the amount of force the driver applies to the pedal. It then instructs the motor to generate as much regenerative braking force, which puts energy back into the battery, as the current driving conditions safely allow. The conventional friction brakes are only engaged to cover the small remaining portion of the required stopping force. In the majority of everyday slowing down situations, this setup means that the regeneration process handles most of the necessary work, often accounting for 70% to 90% of the deceleration in typical city driving patterns. A simple calculation clearly demonstrates why this is so important. A car weighing 1.6 tons traveling at a speed of 50 kilometers per hour possesses 154 kilojoules of kinetic energy, which is equivalent to 0.043 kilowatt-hours. Recovering 70% of this energy returns approximately 0.0303 kilowatt-hours back to the battery pack. In situations involving frequent stopping and starting, such as heavy traffic, these small energy gains add up significantly and are reflected as a clear reduction in the vehicle's energy consumption measured in watt-hours per kilometer. If you happen to find these numerical details and calculations too complicated or overwhelming, you can simply click on the provided link on the screen to access a more detailed explanation of Tesla's regenerative braking technology. I have already provided a very thorough and in-depth explanation of this technology elsewhere. Because the regenerative braking system is responsible for the majority of the stopping effort, the physical friction-based brake hardware, calipers, rotors, can be made smaller without reducing the car's overall safety level. Removing just 1 to 3 kilograms of mass, which is both rotating and unsprung, at each wheel corner has several positive effects. It reduces the wheel's rotational inertia, which allows the suspension system to track and follow the road surface more accurately. And it makes the steering response feel notably crisper and cleaner. This change perfectly complements the motor's ability to produce high torque for every kilowatt, as a larger portion of the motor's effort is translated into genuine changes in wheel speed, rather than being wasted in overcoming unnecessary excess inertia. When the car's system for moving forward, propulsion, and its system for slowing down, braking, are designed to work together perfectly, the result on the road is a vehicle that handles consistently and predictably. The Tesla Model 2 accelerates rapidly from 0 to 50 kilometers per hour, maintains strong pulling power on inclines because the internal iron losses are kept low and the windings remain cool, and it requires fewer kilowatts of power to generate the same amount of turning force at the wheels in mixed driving conditions. Each time the car slows down, a small amount of extra energy is returned to the battery, which lowers the energy use per kilometer, W-hours per kilometer, and increases the overall driving range by a few percent in normal use, and by even more in dense city traffic. The design's flexibility to achieve target ranges with a physically smaller battery pack further contributes to a lower overall vehicle mass while fully preserving the car's lively and responsive driving character. Heat buildup in both the motor and the brakes remains lower, which ensures that both acceleration and stopping performance stay stable and consistent, even through repeated demanding cycles. The rate of wear on the brake pads and rotors is significantly slowed, and the pedal feel remains natural and easy to modulate thanks to the seamless blending of regenerative and friction braking. The design also achieves very low torque ripple, a benefit of the thin laminations and expertly optimized electromagnetics, which keeps the front end of the car precise and stable during maneuvers like changing lanes or merging into traffic. This is precisely the kind of dependable confidence that drivers immediately notice and appreciate from their position behind the wheel. Which specific engineering element of the Tesla Model 2 impresses you the most? A. The very snappy throttle response and rapid launches. B. The regenerative braking system that cuts down W-hours per kilometer and extends the driving range. C. The lighter brake components that make both the steering and the body movements smoother. Please share your choice, A, B, or C. What key factors allow the Tesla Model 2 to travel further, weigh less, drive more smoothly, and have a lower total cost of ownership compared to most Chinese EVs? Second, what permits the Tesla Model 2 to cover a greater distance, have a lighter build, offer a smoother ride experience, and present a reduced overall cost of ownership than comparable Chinese electric vehicles? The Tesla Model 2 utilizes an inverter based on silicon carbide, SiC technology, instead of the older insulated gate bipolar transistor, IGBT design. Silicon carbide components are capable of supporting a much higher switching frequency, allowing for a tight and integrated power module package with a very short DC bus structure. This integrated design successfully lowers the system's effective inductance and resistance. Furthermore, it allows for extremely precise field-oriented control, FOC, of the motor, complete with accurate compensation for dead time. Taken together, these deliberate engineering choices enable the Model 2 to drive a longer distance, weigh less, provide a smoother driving sensation, and offer a lower total cost of ownership than many Chinese EVs that still depend on the older IGBT hardware. So, why does the Model 2 achieve a greater driving range? The ability to use a higher switching frequency results in phase currents that closely resemble perfect sine waves. This reduction in current ripple means that both iron losses and copper losses within the electric motor are significantly decreased. Additionally, silicon carbide devices inherently experience much lower switching loss than IGBTs at the same voltage level. which means the inverter unit itself wastes less electrical power as unwanted heat. Real-world observations frequently show efficiency gains of approximately 1.5 to 3.5 percentage points in the inverter's performance alone. The overall efficiency of the entire drivetrain often increases by a few more percentage points due to the cleaner electrical currents and the extremely accurate field-oriented control. In urban driving scenarios, where the car spends most of its operational time at partial motor loads, this significant improvement is visible as a 3% to 8% reduction in the measured watt-hours per kilometer, the exact figure depending on the specific driving conditions. Consequently, for a battery of the identical size, the Tesla Model 2 successfully delivers more watt-hours of energy to the wheels, thereby covering more distance, or it can achieve the same target range with a physically smaller battery pack. Next, why is the Model 2 built to be lighter? Lower power loss fundamentally means less heat needs to be removed and dissipated, which in turn permits the use of smaller heat sinks, radiators, and circulation pumps for the cooling system. The ability of the SiC devices to switch electrical power much faster also allows for the inclusion of smaller inductors and capacitors in the power electronics. When the main power stage is packaged as compact half-bridge or full-bridge modules with a very short DC link connection, the entire inverter unit shrinks in physical size and can be mounted closer to the motor, further shortening the main DC power path. For a vehicle in the small to medium-size category, these detailed optimizations can remove approximately 4 to 10 kilograms of mass from the overall drivetrain assembly. Reducing the total mass naturally leads to better energy consumption and provides the car's chassis with a more inherently agile foundation. This advantage becomes even more pronounced and clear in extreme weather situations. Many budget-focused Chinese electric vehicles still rely on split cooling, heating loops, and are forced to use energy-intensive resistive heaters for the battery, a method that severely cuts into efficiency when temperatures drop below -10 degrees C or rise above 35 cc. The Tesla Model 2 pairs its sophisticated two-way heat pump with a system of predictive battery preconditioning, which automatically warms or cools the cells before the car is plugged in for a fast charge. This critical step reduces the chance of lithium plating, keeps the charging power stable and high throughout the session, and significantly extends the lifespan of the battery cells. In real-world winter or hot summer driving, the usable driving range can be increased by as much as 20% to 25%, and the cabin reaches a comfortable temperature much faster than with less advanced systems. This is precisely why the Model 2 possesses the capability to alter the marketplace. It is the result of an efficient drive unit, silicon carbide power electronics, a highly flexible battery pack, and a smart thermal loop, all functioning in complete and effective synchronization. Do you happen to know anyone who currently believes that Chinese electric vehicles are impossible to surpass? Tag them in a post